Alright, in this night show, we're going to look at the oscillation, the energy in simple harmonic motion, how are the different types of energy related with each other, and how do the energy transformations take place. Okay, now for considering an ideal pendulum, for example, which form do you think it will have when it is displaced from the equilibrium position, one of the two extremes? Which form of energy it will when it's moving through the equilibrium position? Which forms of energy will it have during the rest of the cycle? And how does the total energy change during the cycle? Well, for answering these questions, well, the object has the potential of fall, so we are considering the potential energy, gravity. It is also moving, so we definitely have kinetic energy, and everywhere where it is moving, it has either potential to fall further or kinetic energy. Okay, so they're going to like transform in a continuous way. So how is that related, in our SHM? The total energy does not change. So between the extremes, to say so, and the equilibrium point, there's a mixture of EP and EK, and the energy is the total energy remains the same. Okay. Okay, how does it relate for springs? Well, they're exactly the same. Apart from the potential energy, we would have elastic potential energy stored in the spring and rather than gravitational. And we have the same conversion between potential and kinetic energy. And you could sketch a graph, okay? Well, if we look at the conservation of energy, that means that the total, and we are considering the spring on a horizontal plateau, the total mechanical energy is U plus K, and this is a system that is oscillating, So for any 2 points, we may write for at position A, for example, mv a square plus half k a square equals to half mvb square plus half kx square. So in total they are the same, only due to the position the values of the kinetic energy and the elastic energy is changing. Now when we look at the energy transformation, whether it's kinetic energy or elastic potential energy or gravitational energy, we see that at extreme sides the potential energy is maximum, there's no movement, meaning there's no kinetic energy. When we move towards the equilibrium, there is no potential energy and the kinetic energy is maximum. The total energy overall will not change. And let's look at this example of the applet and how it actually changes. We will look again at this pendulum and we're going to see how the different types of energy relate. We have the kinetic energy, the potential energy, and we have the total energy. Okay, we're not talking about thermal energy because I'm not going to put any friction. And I let it go. Of course, the potential energy is going to increase. That means this is my total and I let it release. So we see at equilibrium we get a maximum of kinetic energy and the potential energy is gone. But as we see, the total energy is not changing. Put some more gravity. More. Okay. Yep. So we can equate the conservation of energy. In an ideal world, we have no loss of energy at extremes. Plus minus A amplitude one side or the other side. The total energy is equal to EP and EK is 0. When we pass through the equilibrium, the energy equals to the kinetic energy, while the potential energy is 0. And between the 2 points, we may say that the total energy is EP plus EK. Okay? Yeah, we know EK is half mv squared, gravitational energy is mg delta h, and we have the potential energy stored in the spring is half F delta L. Okay, that's it for the energy. And in our next slideshow, we will talk about damping oscillations in short.